Next we have example 31, where we look at the sum of two dice. One die is fair, the other weighted. So the experiment is roll a fair die and a weighted die and record the up faces. The weighted die is constructed in such a way that the probability that the die lands with a given face upwards is proportional to the number of pips on that face. Let the random variable x be the sum of the two up faces. And so in this example, we're going to determine the sample space of x. We'll then find the PMF of x and graph the PMF. And then finally, we'll find the CDF of x and graph the CDF. Now, as in the previous example, the sample space of this experiment is given by the set of ordered pairs I, j, where I ranges from 1 to 6, and also j ranges from 1 to 6, with the structure of an elementary event, ij, being as follows. I is going to be the number obtained on the weighted die, and j, the second coordinate, will be the value obtained on the fair die. Then the random variable x maps this sample space S into the real line in the following way. The random variable applied to an elementary outcome, I, j, is the sum of the two coordinates, I plus j. So it's the sum of the value obtained on the weighted die and the value obtained on the fair die. Now, because the dice in this example are not both fair, the 36 elementary outcomes in the sample space S are not equally likely. Now here I have a table as we had in the previous example, and this shows the sample space, the 36 possible elementary events for this experiment. And so in this example, the columns, which represent the outcomes for die 1, will correspond to the values obtained on the weighted die. So again, we have values 1 through 6. And the rows correspond to the value obtained on die 2, which in this case is the fair die. And so we have the 36 ordered pairs, the elementary events for this experiment. In the previous example, these 36 outcomes were equally likely. They each had a probability of 1 over 36. And that followed from the independence of the dice, as well as the fairness of both dice. But in this example, these 36 elementary outcomes are not equally likely because die 1 is a weighted die. And so in order to calculate probabilities of events associated with this experiment, we're not going to be able to just count the number of ways that the event can occur and divide by 36. We're going to have to use a more detailed approach. So the set of possible values that can be taken on by the random variable are again what they were in the previous example, the integers 2 through 12. And so the question is, how do we find the PMF? Now remember that the PMF is a function f that assigns or determines or provides the probability associated with each of these values in the sample space. So the question is, how do we find this? Well, we have to use what is given to us in the statement of the problem. In particular, one die is fair and the other one weighted in such a way that the probability that the die lands with the given face upwards is proportional to the number of pips or dots on that face. And so that's the information that we have to use in order to find these probabilities. And also we'll use the fact that because the two dice are not connected in any way, the outcomes of the two dice are independent. So because the elementary events comprising the underlying sample space S for this experiment are not equally likely, we cannot use the approach used in the previous example where we counted the number of ways that an event can occur and divide by the number of elementary events in the sample space in order to compute these probabilities. So this is what we were saying a few seconds ago. And so the first step will be to compute the probability associated with each elementary event in the underlying sample space S of the experiment. And again, remember that the reason that we are we have to do this. And let me go back to this table here. Probabilities involving the random variable x, which are going to be the values given by the PMF. In order to determine those probabilities, we have to go back and relate that to what is going on. We have to relate it to the probability structure of the underlying experiment. So probabilities involving a random variable based on which is a function from a sample space of some experiment to the real line. Probabilities involving such a random variable follow from the probability structure on the sample space of the underlying experiment. So that's why we have to determine the probabilities associated with each of these 36 elementary outcomes in the sample space of the original experiment. All right, and once we do that, then we can find the probability structure on the sample space of the random variable x itself. So let's consider first the weighted die only. Again, it is constructed in such a way that the probability that it lands with a given face upwards is proportional to the number of pips or dots on that face. So let R be this constant of proportionality. Then for each k going from 1 to 6, the probability that the weighted die is equal to k is going to be equal to R times k. Again, where R is this proportionality constant, and k is the number of pips that show up when we roll the die. This is what it means for the for the face to the number of pips showing to be proportional. I'm sorry, for a given face showing being proportional to the number of pips on that face. Now we can use this to find the proportionality constant R. So, and to do this, we're going to go back and use some axioms from our axiomatic approach to probability, because that's the structure under which we are working right now, is that axiomatic approach, this most general approach to probability, to the probability calculus. And so note the following. By axiom 1, the probability of the union of the events with the weighted die being equal to k, k going from 1 to 6, the union of that union of events is equal to 1, because this constitutes the union of these events, k going from 1 to 6. All right, and so these events being the weighted die being equal to 1, or the weighted die being equal to 2, or the weighted die being equal to 3, and so forth up to 6. That constitutes the sample space for that particular die, the weighted die. So that exhausts all the possibilities. So this event, this union of events, is the sample space for the weighted die. And so by axiom 1, the probability of that event, the probability of the union of these individual events then, is equal to 1. Now, by axiom 3, because these individual events that are being combined via union to get the sample space for the weighted die, these individual events are mutually exclusive. They're disjoint. And so by axiom 3, the probability of the union of these mutually exclusive events is equal to the sum of the probabilities of the individual events. Now, the probability that the weighted die is equal to k by the result given on the previous slide, which again is right here, that is equal to R times k, this proportionality constant times the particular outcome that we're talking about. Now R does not depend on k, and so we can pull R out of that summation. All right, and so we're left with R times the sum of the k's, k going from 1 to 6. Now that is equal to 21. You can easily verify that. And so we have that 1 is equal to r times 21. Well, now we can solve that for the proportionality constant r. And so we have that this proportionality constant r is equal to 1 over 21. And so from this, we can combine this with the formula for this probability that the weighted die is equal to k from 2 slides ago. We can put that together with that equation, or that formula. And so the probability that the weighted die is equal to k over 21. All right, k going from 1 to 6. And again, it's easy to verify that these probabilities for k going from 1 to 6 add up to 1. All right, now next we consider the fair die. And by calling the die fair, what is meant is that the probability that the fair die is equal to any of the values from 1 to 6, they're all equal to 1 over 6. So that's easy, and we actually, we used that in the previous example, so that one's easy to obtain. And then finally, we consider the joint outcomes involving the two dice. Since the dice are not connected in any way, but are allowed to roll independently of each other, the outcomes of the two dice can be assumed to be stochastically independent. So that's a completely valid assumption here. And so based on that, we can use the information about the probabilities of the two dice individually and put them together jointly to get probabilities of joint events. So for k going from 1 to 6 and j going from 1 to 6 as well, the probability that the weighted die, one way we can read, well, let me read 2 ways. The probability that a particular outcome, an ordered pair, where again the first coordinate is the weighted die, the second coordinate is the fair die, being equal to the ordered pair k comma j. All right, so this is equal to, or equivalent to, the probability that the weighted die is equal to k intersect with the fair die is equal to j. And remember, we can read that as and, so this is the probability that the weighted die is equal to k and that the fair die is equal to j, all right, by independence. And again, it's reasonable to assume that the results of the two dice are independent because they're not connected in any way. So the probability of this joint event, and again, it's a joint event because we have intersect here between these two events, by independence, this is equal to the probability that the weighted die is equal to k times the probability that the fair die is equal to j. So we've decomposed this probability of a joint event as the product, right, there's the product, of the probabilities of the individual events involving the individual dice. Well, we have formulas for each of these probabilities. The probability that the weighted die is equal to k, we found to be k over 21, and the probability that the fair die is equal to j is equal to 1 over 6. And so multiplying those together, the probability of this joint event, all right, is k over 126. All right, now consider the sample space of the original experiment S, and for each k going from 2 to 12, we're again going to consider the events which we'll denote by A sub k, which consists of the ordered pairs I comma j, where the sum of the two coordinates, the sum of the two dice, is equal to k. And we looked at this notation and this representation in the previous example. All right, and it's going to be useful for this example as well. And so then these events can be expressed as subsets of the sample space cap S in the following way. And you'll remember from the previous example that we had the same representation for these events. All right, so we have the events labeled A2 through A12. All right, and then we've also got representations of those events in terms of the elementary events that comprise those events, or in other words, as subsets of the sample space. Now, these events can also be expressed as unions of elementary events, all right, which I think is fairly straightforward and obvious, but it's going to be useful notationally when we go to calculate probabilities. So, for example, the event A3, which expressed as a subset of the sample space, is the set of ordered pairs 1, 2, and 2, 1. This can be expressed as the union of two elementary events, the union where k goes from 1 to 2, of the elementary event k, 3 minus k. All right, so when k is equal to 1, we have 1, 2, and when k is equal to 2, we have 2, 1. And that's exactly what we have right here. Similarly, A4, which expressed when expressed as a subset of the sample space, consists of the three elementary events, 1, 3, 2, 2, and 3, 1. This can be expressed as the union of elementary events, k going from 1 to 3, the union of elementary events k, 4 minus k. So when k is equal to 1, we have the elementary event 1, 3. When k is equal to 2, we have the event 2, 2. And when k is equal to 3, we have the event 3, 1. And that's exactly what we have here. And so likewise, each of these composite events can be expressed as unions of elementary events according to these formulas. Now, I want to make this clearer, so in the next slide I'll just get rid of the representations based on subsets of the sample space and just look at how these are represented as unions. And so this allows us to focus on this particular type of representation. And this is useful because it's going to be helpful when we go to calculate probabilities. So for example, we want the probability of A2, and so that's going to be the probability of that event right there. We're going to want the probability of A3, so that will be the probability of this union, and so forth. And so then on the next slide, we can begin to calculate those probabilities. So using the formula that was derived on a previous slide, the probabilities for each of these events, so the probability that x is equal to k going from 2 to 12, are then calculated as shown below. So for example, the probability that x is equal to 2, according to this formula that we derived, is equal to 1 over 126. Now that one's easy to do because we only have one elementary event whose probability we need to determine. Now, using axiom 3 and the fact that the elementary events are mutually exclusive, which they are, then the probability that x is equal to 3, which is equal to the probability of A3, is then going to be the probability of the union, k going from 1 to 2, of these elementary events. All right? And so then, by axiom 3, because these elementary events are mutually exclusive and they're then put together or combined with union, by axiom 3, the probability of the union of events is just the sum of the probabilities of the individual events. Now, so for example, the probability, well, to compute this probability or to come up with the expression, we go back to the formula that we derived on a previous slide. And so the probability that the weighted die is equal to k and that the fair die is equal to 3 minus k is k over 126. All right, now we can rewrite that as 1 over 126 times k, and then the 1 over 126 can be brought outside of the summation, so we then just have the sum of the k's. And so this would be 3 over 126. So the probability that x is equal to 3 is equal to 3 over 126. Now this calculation and its justification is a model for the calculation of the rest of the probabilities. And so we'll just write those down here without going into a lot of detail. And so the probability that x is equal to 4 is equal to 6 over 126. The probability that x is equal to 5 is 10 over 126, and so forth. All right, and finally, down here for x equal to 12, the probability that x is equal to 12 is equal to 6 over 126. Now, in each one of these rows here, or lines, calculations, we have this notation here. All right, and this just this is a shorthand way. It's an abbreviation of saying or indicating that the equality going from here to here is justified by axiom 3. And again, it's justified by axiom 3 because we have on the left-hand side of that notation, we have the probability of a union of events, and those events that are being unioned together are mutually exclusive. Now, we've derived the probability for x being equal to each of the values in its sample space, and every step in each calculation is justified. All right, and that's important. This is a theory class, and what we're focusing on is being able to justify everything that we do. All right, and so make sure that you understand the justification in each one of these steps. All right, so we can now write down the PMF, and expressed in piecewise fashion, as we've been doing up to this point, we can write it down this way. And so we have the sample space of x, script A, consisting of the integers from 2 to 12. And so for each of the values in the sample space of x, we've listed the probabilities that we just calculated. And then to complete the specification of the PMF, we have to indicate that for any other value at which we would evaluate this function, it returns a value of 0. So a few things to point out about the PMF. It's defined at every real number on the real line. It is strictly positive at every point in the sample space of x, whereas it's 0 at any point not in the sample space of x. All right, and so what does a graph of this PMF look like? Well, again, it is looks like a histogram. All right, it's a collection of rectangles. Each rectangle corresponds to a particular value in the sample space of the random variable. Each rectangle is centered over the value to which it is associated. And the area of each rectangle is equal to the probability associated with each of those outcomes. And so the sample space consists of the values from 2 to 12. And so we have rectangles centered over each of those values. And then in addition to that, I've shown the probabilities, rounded to 3 decimal places, of each of these values in the sample space. And again, those are also correspond to the areas of those rectangles. All right, and you'll notice that these values add up to 1, as they should. All right, then we can find the cumulative distribution function by accumulating probabilities as we march down the real line. All right, and so we know that before we get to 2, we've not accumulated any probability, and so the CDF evaluated at a value of x that is strictly less than 2 will be 0. Once we get to 12, we've accumulated all the probability that there is to accumulate, and so the CDF evaluated at any value of x that is greater than or equal to 12 will be equal to 1. And then at values of x that are between greater than or equal to 2 and strictly less than 12, then it would depend on where we are. All right, and this is what we get. So make sure, we're not spending as much time on deriving or determining the CDF, but I think it's fairly straightforward. But make sure that you can do this. All right, and then what does the graph of the CDF look like? Well, before we look at the graph, let's just point out that the CDF, the way that we've specified it, it is defined at every real number, which it needs to be. It is a non-decreasing function, right? It's either increasing or staying constant, but as we go to the right, as x increases, it never goes down. It is equal to 0 at every point to the left of the smallest point in the sample space, which was 2, right? So that at every value of x less than 2 or to the left of 2, the CDF is equal to 0 because we've not accumulated any probability yet. And then it's equal to 1 at or to the right of the largest point in the sample space, which was 12. And so for any value of x greater than or equal to 12, the CDF evaluates to 1. And so here is a graph of the CDF. All right, you'll see that it's a step function, all right, as they have been before. And again, I'll just point out that the step height is equal to the probability associated with that particular value in a sample space. So the height or the jump in going from here to here is the probability associated with x being equal to 7. Now, I also wanted to show you, let's see here, this table, like we had before, but in this case what I've done is I've filled in these probabilities, all right, based on the formula that we determined for the joint probabilities. And so you can see here, again, the columns correspond to the outcome of the weighted die. The rows correspond to the outcome of the fair die. And then you can see the individual probabilities for these cells. We've got 36 possible outcomes in the sample space of the underlying experiment, all right, and the probabilities of these individual outcomes, or these elementary outcomes, are given by the values in this table. So that wraps up example 31. In the next lecture video, we're going to get into continuous random variables. So I'll see you then.